Chapter 7 of History of Chemistry, Volume 2, by Sir Edward Thorp. This LibriVox recording is in the public domain. Valency. Chemical formulae from the time of Berzelius onwards have been regarded as rational expressions. That is, they serve to represent the relations and analogies of the substance they are employed to designate, and indicate in the simplest and at the same time the most comprehensive manner the chemical changes in which the substances take part. In the words of Gerhardt, those formulae are, quote, "the best that make evident the greatest number of such relations and analogies," unquote, and that serve to express the greatest number of the chemical changes in which they are concerned. In such concrete expressions of chemical change it was frequently observed that a definite group of some or all of the constituent elements of the substance hung together, as it were, and passed apparently unchanged into the products of its transformation. These groups were not necessarily radicals in the sense in which Liebig and Wöhler used the term. To Gerhardt and to Kekule, they were simply residues, remaining unattacked in a chemical metamorphosis, and passing as such into the products of the change. They might or might not be capable of isolation as definite entities. Thus, for example, we may represent the composition of the following sulfur compounds so as to show that they all contain the group SO2, or sulfuryl: SO2Cl2, sulfuryl chloride; SO2ClOH, chlorosulfonic acid; SO2NO2Cl, sulfuryl nitrile chloride; SO2NO2OH, leaden chamber crystals; SO2OHOH, sulfuric acid. These formulae serve to show how the several substances are mutually related, and that they may be derived from one another by the substitution of atoms of chlorine for hydroxyl, OH, or nitrile, NO2, or vice versa. It was pointed out in 1851 by Williamson and subsequently by Gerhardt that these groups are characterized by differences in their power of combining with or replacing atoms of hydrogen, or of groups or elements which, like chlorine, are chemically equivalent to hydrogen. Such a radical or residue as ethyl, carbon 2 hydrogen 5, C2H5, is chemically equivalent to one atom of hydrogen, as is shown when we compare the formula for ether as established by Williamson with that of ordinary alcohol: C2H5H O, alcohol; C2H5 C2H5O, ether. Sulfuryl, SO2, is chemically equivalent to two atoms of hydrogen; phosphoryl, PO, as suggested by Odling, to three atoms of hydrogen. Gerhardt therefore proposed to designate these and similar groups as monatomic, diatomic, triatomic, according to their respective hydrogen replacing power. This conception of the definite atom fixing or replacing power of groups or compound radicals was extended by Frankland in 1852, so as to include the simple radicals, that is, the elements. In the memoir in which he announced the existence of the organometallic compounds, he pointed out that the elements may be classified according to their combining power, or, as he expressed it, according as, quote, "their affinities are best satisfied," unquote. This idea was independently developed by Cooper and Kekule in 1858. It is from that period that the definite introduction of the conception of atomicity, atomic value or valency, into chemical doctrine may be said to date. The memoir in Liebig's Annalen der Chemie und Pharmacie, in which Kekule announced his views, deals particularly with the tetravalency of carbon and the doctrine of linking of atoms in terms of their valency. As formulated by Kekule and as subsequently developed in his famous textbook, this doctrine exercised an immediate effect on the progress of the chemistry of carbon compounds. Like every fruitful hypothesis, it stimulated inquiry and brought out analogies, and the more it was applied the more apparent became its suggestiveness and utility. The scope of chemical formulae was greatly extended. Rational formulae grew into dissected or constitutional formulae, and on the system of constitutional formulae have been grafted successive attempts to elucidate the manner in which the constituents of a molecule are grouped and held together. It is interesting to note that the proximate effect of the theory of chemical structure which grew out of Kekule's doctrine was to assimilate what was sound in the seemingly antagonistic theories of types and radicals. As a mode of exposition, Kekule used models to illustrate the manner in which the affinity values of compounds are satisfied. These were not intended to represent the actual spatial distribution of the atoms in a molecule, but they nevertheless familiarized the mind with the idea first clearly recognized by Wollaston and Berzelius, that this is the ultimate aim of chemistry. It was probably their use, either actually or by visualization, that led Kekule in 1865 to his theory of the constitution of benzene, as developed in his paper on the constitution of aromatic compounds, a theory no less fruitful in its consequences than that of the tetravalency of carbon and of the linkage of atoms. Such models, too, in the hands of Van 't Hoff, subsequently served to elucidate the connection between optical characters and crystalline form, and to explain the isomerism of certain organic substances. Kekule was of opinion that the valency or affinity value of an element was a definite and invariable quantity, a fundamental property of the atom as immutable as its atomic weight. Many facts appear to show that such is not the case. Thus phosphorus and nitrogen are sometimes trivalent and at other times pentavalent. Tin, in certain of its compounds, is divalent, in others tetravalent. Sulfur may be a dyad, a tetrad, or a hexad. It will be seen that the valency of these particular elements varies by 2 units. This was at one time held to be a natural law, and the various elements were divided by Franklin into 2 main groups of 1. Perisads, or elements of odd atomic value, and ardyads, or elements of even atomic value. Experience has demonstrated that a rigid classification on this basis is not possible. Many instances are known of elements not only varying in valency by 2 units, but even by 1 unit. Thus nitrogen, which is usually a perisad, is apparently an ardyad in nitric acid and in gaseous nitrogen peroxide. Roscoe has shown that uranium and tungsten, originally regarded as ardyads, form pentachlorides. To what the difference in the affinity value of an element is due, and why different elements should manifest different values, is at present unknown. Valency, like other properties, appears to be a periodic function of atomic weight, from the behavior of such analogous compounds as phosphorus pentafluoride, phosphorus pentachloride, phosphorus pentabromide. It seems, too, to be related to the weights of the atoms in combination. Further, it would appear that the mutual affinities of substances vary with temperature, that is, with the energy imparted to their molecules. Numerous instances appear to indicate that the atom-fixing power of an element decreases when it is strongly heated, that is, when the internal energy imparted to its combinations exceeds a certain limiting value. Van 't Hoff has attempted a mechanical explanation of valency depending on the shape of the atoms, as affected by variation in their vibratory motions resulting from differences of temperature. Helmholtz suggested that the different charges of electricity associated with the atoms may determine their affinity values, that, for example, a monad carries a single charge, a dyad 2, a triad 3 charges. Many considerations go to show that the affinity value of an element is not capable of definite numerical expression in the sense which the doctrine of valency as generally understood implies, and that the variations are not of the per saltum character assumed by saying that the affinity value is sometimes 1, sometimes 2, at other times 3, and so on. When we have apparently satisfied the accepted atomic value of an element by allocating to it what we regard as the necessary complement of atoms of other bodies, it is frequently evident that the capacity for combination of the whole molecule is not satisfied. Many apparently saturated molecules have the power of combining with other equally saturated molecules. Sulfur trioxide, SO3, and barium monoxide, BaO, would appear each to have their affinity values satisfied. Nevertheless, they combine with great readiness to form barium sulfate, BaSO4. End of chapter 7.